Okay, so here I'm going to work a problem using DeMoivre's theorem. DeMoivre's theorem is just a theorem. It's just basically a formula that you can use when you want to raise your complex number z to a power. So you use this formula, z to the n is equal to r to the n cosine n theta plus I sine n theta. It's pretty straightforward. You just basically plug your complex number and your power into this formula and simplify, and you will get, you will simplify the power. Okay, so let's practice with this problem. If you're asked to write the expression in the standard form, a plus bi, and do you see that we have a complex number here raised to a power? Do you see that this complex number is raised to the fifth power? I'm going to rewrite, hold on, I'll do this without taking the time. Okay, so I've pasted DeMoivre's theorem, the formula, up here for us to use when we are simplifying this complex number that's being raised to a power of 5. Okay, so we're going to say, in this case, this is our z, so this is going to be z to the fifth equals r to the fifth, so 2 to the fifth, times cosine 5 times pi over 5, plus I sine 5 times pi over 5. Too many parentheses there. Now what we want to do is simplify. So z to the fifth equals 2 to the fifth is 32. We've got cosine, and 5 times pi over 5 is just pi, plus I sine pi. Now, looking at this, we can simplify further. Z to the fifth equals 32 times cosine of pi. If you think about that, remember pi on the unit circle, it's right here. Negative 1, 0. Cosine is the x value, so the cosine of pi is going to be negative 1, plus I times the sine of pi. The sine of pi is the y value at, what am I doing? Sorry. The y value at pi, which is going to be 0. So now, if we simplify this further, we get z to the fifth equals 32 times negative 1 plus 0. 0i is 0. And if we distribute, we get z to the fifth equals negative 32. And do you see that we had a complex number, a number that involved non-real numbers, raised to the fifth power, and in raising it to the fifth power, we took a number that involved non-real values and reduced it down to a real number. C to the fifth is equal to negative 32, which is a real number. Okay, so now we're going to do one more problem. This problem actually involves degrees. Okay, and I just attached the formula again so that you can have an idea of where these values are coming from. So if we want, in this case, this complex number is being raised to the sixth. Whoop, what's going on here? Okay, trying again. This complex number is being raised to the sixth power, and you see that right there. So let's find z to the sixth power. We say r, which is going to be square root of 5, to the sixth power, cosine 6 times 35 degrees, plus I sine 6 times 35 degrees. Okay, so now we have to simplify, and in simplifying we get z to the 6 equals root 5 to the 6 is the same thing as saying 5 to the 1/2 to the 6th power. And we've got cosine of 6 times 35 is 210, plus I sine 210. Okay, so now step 3, z to the 6th equals 5 to the 1/2 to the 6th. Remember, when you have a power to a power, you multiply the two powers together. So 1/2 times 6 gives us 3, so this is going to be 5 cubed. Cosine 210 plus I sine 210. 2 looks kind of funny. Can you read that? I'll erase it. Sine 210. Okay. So if we continue simplifying, z to the 6 equals 5 cubed is 125. Cosine of 210, if you look on your unit circle, you would get, negative root 3 over 2 plus I times the sine of 210, and if you look on your unit circle, the sine of 210 is negative 1/2. So if we continue to simplify here, distribute our 125, we get z to the 6th equals negative 125 root 3 over 2, or minus 125 over 2i. And that is correct. So this is our value of z that was given to us raised to the 6th power. And we raise it to the 6th power using DeMoivre's theorem, which is a pretty straightforward formula. I hope this helps. I hope this makes sense to you. We'll talk more about this in class on Thursday.